All right, let us get started. Quantum jobs of tomorrow. What do you need to know today? I am Dr. Svetlana Barkanova, Professor of Physics, School of Science and Environment at Grenfell Campus Memorial University of Newfoundland and Labrador, Canada. And this is our beautiful observatory. Well, as you probably guessed by now from my name and my accent, I am not from Newfoundland originally. I grew up in Latvia. This is our capital city, Riga, beautiful, about 800 years old. This is my alma mater, that building on the top right corner. Uh, most of my classes were on the fourth floor and no elevators. So I got my undergraduate and master's degree at the University of Latvia, worked on various research projects in Latvia, Scandinavia, Germany, and eventually moved south to Canada. And now I am on the beautiful west coast of Newfoundland, and I absolutely love it there. Have a look. That is a view from Grossmore National Park. The scenery is stunning. People are wonderful. The weather is better. And now as a professor of physics at Memorial University of Labrador, Newfoundland and Labrador, I have the best job in the universe. I teach really cool courses such as astrophysics, quantum physics, subatomic physics. I work on fascinating research projects. One of them is trying to figure out the nature of dark matter. And recently, I was also selected as one of three inaugural chairs for inclusion in science and engineering in Atlantic Canada, established and funded by Natural Science and Engineering Research Council of Canada. So thrilled to be there. And again, thanks for joining me. Now, this year is especially exciting for me because it's the International Year of Quantum Science and Technology, which is celebrating 100 years since the initial development of quantum mechanics. 100 years, wow. And it is just the beginning. Here's a website. You can see it on your screen, quantum2025.org. This is the central international website about all of the events worldwide, but we also have our own in Canada. I'll show it to you in a moment. Careers in quantum science and technology now include research, engineering, software development, business applications. Have a look. Research, for example, fundamental physics. That's what I do. I work in theoretical particle physics, so that's fundamental physics, and it's very much quantum. There's also quantum computing theory, quantum materials, quantum information science. If you look on engineering side, there's hardware development, cryogenics, photonics, electronics design, systems integration. Software development, quantum algorithms, quantum programming languages, hybrid quantum classical systems. This is especially interesting. Quantum and regular computing, error correction and optimization, and of course, business applications which are multiple, such as cybersecurity. We are just getting started. The Canadian Association of Physicists, of which I am a proud member, and if you're a physicist, I hope you will join, we are celebrating as well. And one of the projects we did to start with is to invite physics students in Canada to develop a logo. And here is a logo developed by a winner, Jasmine Zhang, first year PhD students from UBC Triumph. So here you can see superposition of technological advancement and a natural world. And the flipped on the maple leaf is a nod to orthogonal basis for spin one half particles, now one up and one down. Beautiful, isn't it? So starting on the World Quantum Day on April 14, 2025, which was double exciting for me because it's a World Quantum Day on April 14th. That's always on April 14th. But also this year is International Year for Quantum Science and Technology. And what we did is working together as NSERC Chairs for Inclusion in Science and Engineering in Atlantic, Canada, and International Year of Quantum Science and Technology group hosted by the Canadian Association of Physicists. Together, we are thrilled to present Canadian experts offering weekly online talks on quantum science and careers for grade 10 to 12 students. So the level is developed for grade 10 to 12, but everyone is welcome. Our first talk was on April 14th. This is the second, and we're going to do that every week. So you're going to see the list at the CISE-Atlantic website. This is CISE-Atlantic, Cheers for Inclusion in Science and Engineering Atlantic. And there are also a wide range of Canada initiatives or by the Canadian Association Physicists site. So right here you can see it's EYQCDA or at .cap.ca. So two websites you may want to check out for the future events. Our first talk, our inaugural talk for the series on April 14th, was Adventures in Quantum Land, Superposition and Entanglement by Dr. Chitra Rangan, and it is now on YouTube. So you can have a look anytime. Just go on to YouTube, look for Adventures in Quantum Land, and think of that as a foundational talk. If you don't really know much of quantum physics or quantum mechanics, you definitely want to see it first before we dive into application with our series. So we're going to do one talk every week for high school students. But if you missed Chitra talks last week, I suggest you have a look at the YouTube. So it is available at YouTube right now, only 32 minutes, absolutely worth your time. And our next one is by Dr. Connor Kupchak. That's next week. And that's going to be about building a future quantum internet. Now that's really exciting. I'm definitely going to watch that one. So this is next week. Look for that on Eventbrite. You need to register in advance to attend. So go to Eventbrite and just look for Building a Future Quantum Internet talk. Now, I'm a physicist, but physics is such a great field. I actually tried to come up with alphabetic list at first, atomic astrophysics and so on, and just gave up. There's so much to choose from. I work in particle physics, mostly in theory, but it can be as theoretical or as applicable as you can, including quantum physics, electronics, geophysics, medical physics, and so on and so on and so forth. Huge field. Now you all know that guy, right? And I really like this quote of his saying the most fundamental emotion is the mysterious. Fundamental emotion that stands at the cradle of true art and true science. If you're into mysteries of our universe, quantum physics is for you. Definitely still a lot of mysteries we have to work out. Now, here is another famous physicist. We know this one, right? Sheldon Cooper from Big Bang Theory. And in that show, he's a theoretical physicist, something what I do. And if you look at those wiggly lines on the whiteboards, those are called Feynman diagrams. Surprisingly, for a TV show, those equations and those diagrams are correct. Doesn't happen very often. And this is a mechanism I use in my own work. So those Feynman diagrams are very useful in sketching the particle interactions and decays. Now here is another famous physicist, Professor Hubert Farnsworth from Futurama. A kind of classic mind scientist character, isn't he? And here is a course he invented: neutron encrusted, steaming hot dark matter. Kind of what I do. I'll tell you a little bit about my own research before going back to into quantum science and technology careers. So let's dive into a quantum universe. Let's start with our regular matter. You, me, everything you see around. Matter is made out of atoms. Every atom is made out of nucleus and some electrons on the shelf. So here you are in a quantum world, which works really different from our regular everyday world. The rules are entirely different, and it is fascinating. I love it. Then, as you zoom in, you go into nuclear physics. Nucleus is made out of protons and neutrons. As you keep zooming in, every proton and neutron are made out of quarks. So here is a proton, up, and down quark. If you keep zooming in, and this is still quantum world, quantum rules do apply. Well, I don't really know what's in there. We call it new physics. So physics beyond standard model of particle physics. I don't have an image for you, so I'm just using an image of cats. Just cats. I like cats for no reason. So cats. This is a screenshot from one of my own articles. Now, they state I am an internationally known scientist. I guess that's because there may be 10 people who read my publications. They look like that. That's a lot of math. Math is the language of physics. If you want to work in physics or quantum science and technology, you absolutely must master math. Or maybe you just love math and keep doing that. I started by thinking about just studying math, and then at some point it just didn't feel like enough, and I wanted to look into secrets of the universe. So I I continued my studies in physics, but I absolutely love math. I think it's beautiful. Now, let's have a look at so-called standard model of particle physics. It's really elegant, isn't it? Look at that. Look at 6 quarks, 6 leptons, up, down, charm, strange, top, bottom. So quarks are the building blocks of our universe. All the particles in the universe are made out of quarks. To build an atom, you'll need some quarks to make your protons and neutrons, and then you need electrons uh, on the shell, and other particles like electrons, we call them leptons and so on. Now we have interaction carriers, and again, it's all quantum physics, describing 4 fundamental interactions. Well, except for gravity. We actually don't have quantum theory for gravity yet. Gravity works on everything in our universe, everything with mass. Then you have weak nuclear interaction, acts on quarks and leptons. Electromagnetic interaction carries a photon, particle of light, we're all familiar with. Acts on everything with electric charge. And then you have strong nuclear interaction, acts on quarks and gluons. So we have, for interactions, we have quantum theory for 3 out of 4. We don't have a theory for quantum gravity, or at least not yet. And this is why on this forceful spices rack, gravity is kind of on a side. Okay, so we have our quarks, we have our leptons, we have our forceful spices. Are we ready to cook the reality stew? Do we know how to make the universe? As it turned out, not quite yet. There is still a little problem with dark matter. And that's what I'm trying to figure out. That's one of my research projects. I'm really excited about it. So many unanswered questions. Still so much to do. Let's have a look at some. Why does matter dominate over antimatter in our universe? There's way more matter in our universe than antimatter. And yet, according to our most fundamental theory, when you have energy, you can make particles and antiparticles in equal numbers, 50-50. So if that's happened during the Big Bang, where did antimatter go? Where is it? Now, what physics, if any, exists beyond the standard model of particle physics? So we just looked at six quarks, six leptons, fundamental interactions. Is that it? Actually, we know that no. Our standard model of particle physics is incomplete. And we do have experimental evidence to prove that. I'm not saying it's incorrect, it's just incomplete. And the last but not least, what is the nature of dark matter? And I think that it is connected with physics beyond standard model, or so-called new physics. So maybe the particles which are responsible for dark matter are particles like this guy in green, some new particle we still have to discover. So we'll see. This is dark matter. We call it dark because it does not emit, absorb, or reflect light. It's dark. We don't see it. This is not dark matter. What you're looking at here is a galaxy made out of billions of stars. Stars are gigantic thermonuclear fusion engine when they emit light, and that's what we see. Dark matter does not emit light. Would you like to know what dark matter is made of? Yeah, me too. We actually can map it. We know where it is because it interacts gravitationally. And as we are looking for galaxy motion, we actually can calculate its location. So what you see on your left is some random patch of a sky. All of those blobs of light you see mostly in orange, those are galaxies. They're looking kind of reddish or orange because they're redshifted. So all of those are galaxies. Looks normal, more or less even distribution. But then if you look at the same patch of the sky to the right, what that red blob you see right in the center, that means there is lots of mass there. This is mass. More mass is red, less mass is green, almost nothing is blue. Now, let's look to the left again. Do you see anything unusual here? No, looks normal. So there is a lot of dark matter in our universe. It is distributed differently. There is a lot of it, and we still don't know what it is made of. It's kind of jelly beans in a jar. So if you look at the jar, imagine a jar filled mostly with black jelly beans. This is dark matter, and colored jelly beans, those are our regular galaxies. Dark matter makes up the 80% of the matter of the universe. Think about it. Most of the dark matter in our universe is dark matter, but it neither emits nor absorbs light, so its fundamental properties remain unknown. And a while ago, people were saying that looking for dark matter is like looking for a black cat in a dark room and you don't even know if the cat is actually there. Well, it's better now because we do know that cat is indeed in the room. We do have evidence. We just need to figure out what it is. We need to catch it. How? Well, that's where quantum universe come in. Right here in a white circle, this is our visible matter. Our protons, our neutrons, our quarks and muons and neutrinos. That's the matter we are very familiar with. Everything outside of this circle are dark matter. So Can it be neutralinos or dark neutron or axion or weakly interactive massive particles? Well, no one knows yet, but we do have a way to look for them with accelerators, such as Large Hadron Collider in Geneva. This is absolutely amazing research facility. It is underground tunnel which goes under France and Switzerland, 27 kilometers underground. One of our future presenter, Dr. Ruben Sandapen, he's at CERN right now, and he's going to give us a talk a little bit later in French, also about future of quantum science and technology. This is the Atlas detector under construction. Just look at the scale of that thing. You can see a person standing right there in the middle, just to show you the scale. We call it big science. Big machine, big experiments, big science, big teams. And if you want to work in this area, think about developing your collaboration and communication skills as well, because people work in large teams. This is me right there on top looking down at the Atlas detector. So of course everything is underground and you just look down. And this is me at Snow Lab, that is Sudbury Neutrino Observatory in, well, Sudbury, Canada. It is a super clean research facility, 2 kilometers underground. So just go down, down, down 2 kilometers. And look at the walls right here. So that is bedrock painted to make it cleaner, and you need to cover everything with plastic so as not to bring any contaminants in the lab. They do run very, very sensitive experiments there. Here's one of them. What you see here looks kind of like a Death Star, isn't it? This is 3,600 kilograms of liquid argon as a target, which can detect weakly interactive massive particles directly. So that is in Canada, 2 kilometers underground in Sudbury, Ontario. Now, if you are a high school student, think about it. Where do you see yourself in 10 years? So you'll graduate from high school, you do some university, you'll get some job experience. 10 years. Where do you want to be in 10 years? Well, how about 20 years? How about 30? Do you have a plan? Well, it's a trick question. Lots of jobs that will exist in just in 2030, just in 5 years from now, have not been invented yet. It's hard to plan, isn't it? So, how do you prepare for jobs that don't exist yet? Skills. Think in terms of skills. Start on developing those skills right now. But which skills are they? Which skills are you going to need in 5, 10, or 20 years from now? Well, let's look at some trends. So this is a tables from World Economic Forum of skills most valued at the job market. And let's have a look at the changes from 2015 to 2020. In 2015, skill number 1, complex problem solving. Okay, makes sense. Number 2, coordinating with others. Number 3, people management. Number 4, critical thinking. And if you go to the very bottom of that list, number 10, creativity. 5 years from then, 2020, number 1, complex problem solving. Yeah, that's always number 1. You can assume that's safely enough. Critical thinking is now number 2, and creativity is number 3. Look how things change. Let's go from 2020 to 2030. Well, I'm just guessing here, but I asked ChatGPT to help me with some analysis, and here is a list. Uh, Analytical thinking or complex problem solving, absolutely. Creative thinking, resilience, flexibility, motivation and self-awareness, curiosity, technological literacy, of course, dependability, empathy, leadership, and quality control. Now, what kind of education is going to give you those skills? Well, I have a suggestion: physics. And from my own experience, physics is emphasizes problem solving and abstract thinking. So it's analytical thinking, creative thinking. And so you're going to get flexible skill set, which opens door to a wide variety of career paths, not just physics, not just research, engineering, computer science, a whole bunch of career paths, because you develop most of those skills. So, okay, fairly enough, I don't think we are doing really good with empathy and leadership and social skills in physics, but maybe we should. Maybe we should think about that as well. So yeah, all of those skills in blue, you develop those skills for the future if you study physics. So if you're in high school, those are some core subjects which you may want to take. Number one, mathematics. You absolutely need it. Mathematics is a language of physics, language of science. If you are thinking about a career in quantum science and technology, you need to master mathematics. Algebra, geometry, trigonometry, pre-calculus, and later calculus. Number two, physics. In high school, you're going to study classical mechanics, electricity and magnetism, which is critical for quantum devices, and of course, wave and lights. Think photons. Photons are particles of light and they're key to quantum technology. Computer science, if it is available in your high school, absolutely do take some coding or computer science. Learn coding basics in any language, does not matter. Just get the idea. Start thinking about logic, algorithms, problem solving. Chemistry is optional but helpful if you have an option. A special atomic theory and electron behavior. It kind of builds some quantum intuition. So chemistry is helpful. And number five, English and communication, because you will need strong reading and writing skills to help you later for explaining complex ideas. I must admit, when I was in high school, I made a mistake thinking that languages are not important. I wasn't really paying attention. I was so excited about all of that physics and mathematics. I wasn't really paying much attention to my literature classes. And I regret it now because scientists must communicate too. And strong communication skills are super important. So here is a typical journey for into quantum science and technology for if you start in grade 10. So grade 10 to 12, math, physics, coding basics. Chemistry, if you have that option, communication skills. At the university, as you're getting your undergraduate degree, think physics, computer science, engineering, or math major, or some combinations. Some Canadian universities are actually offering joint degrees. For example, on my campus, this is Grenfell campus, Memorial University of Newfoundland, we offer joint physics and math major. Or sometimes there is physics and engineering or physics and computer science. Then, optional, You may want to continue into graduate school to get your master's or PhD, and then you're actually going to specialize in quantum science and quantum communication and quantum engineering. What kind of career are you going to have? Research, that's what I do. I really enjoy it. Tech industry, government lab, startups, health tech, quantum security. There are so many options. If you are in Atlantic Canada, we have a whole bunch of universities which are offering degrees in physics, and sometimes again combined with math, sometimes they're combined with engineering. So there's a whole list. You have Dalhousie University in Halifax, big school. St. Mary's University has its own observatory. Acadia University, close mentorship, undergraduate focus. St. Francis Xavier, good foundation in solid state physics, nuclear and medical. University of New Brunswick, quantum optics, material science, engineering physics, so you can get a degree in engineering physics. Mount Allison, strong undergraduate focus, has interdisciplinary options. Memorial University in St. John, that's our main campus, quantum physics, ocean physics, atmospheric science. Memorial University Corner Brook campus, quantum physics, subatomic physics, undergraduate research. We have very small classes. And University of Prince Edward Island, really good foundations and very supportive environment. You have a lot of options. They're all great. Make your pick. And just because you get a degree of physics, it doesn't mean you're going to be a physicist. Some of the physicists work in engineering. Other sciences, technology, math, or even non-STEM. So physicists often get a wide, choose a wide career paths. Salaries, as you can see, not bad at all. And they're just for physics. If you get a degree in engineering or mathematics or chemical engineering, so they're all great. Just think STEM fields. And if you're in grade 10, 9, 11, probably you can decide now. And you don't have to. Just start your first year at university, take some physics, math, chemistry, coding classes, see what you like, and take it from there. This is top 5 career in quantum science and technology. And the list goes on and on and on. I don't have time in this talk to go over all of them, but it's easy to find online. Just look at some of the options. Quantum software development. That sounds cool. Building quantum algorithms for quantum computers. Quantum hardware engineer. Designing and maintaining quantum processors using superconductors, trapped ions, photons. That needs physics and electrical engineering. So think of degree which can give you both. And again, there's a lot of degrees which are combined. You don't have to choose between physics and engineering. You can do both. Quantum algorithm researcher. In inventing new ways to solve real-world problems with quantum computers, finance, chemistry, logistics. By the way, one of our upcoming talks is going to be in quantum finance. Isn't that cool? Again, you need heavy math, you need computer skills, and you absolutely need creativity. Quantum cryptography expert, creating unbreakable encryption. So that is a huge field for cybersecurity. And quantum machine learning specialist, combining artificial intelligence and quantum computing to make smarter, faster machine learning methods. I think that is going to be a huge interdisciplinary field in the future. And this is just some suggestions. The world is changing fast. Nobody really knows what kind of careers you're going to have in 10, 20, or 30 years. But think of skills: creativity, analytical thinking, problem solving, and flexibility. Now, this is one of our graduates from Grenfell Campus Memorial University who did her undergraduate research in subatomic physics, doing what I do, particles and interactions. But later she went to get her graduate degree in the Netherlands, and she was using supercomputers to simulate the atmospheric boundary layers and large-scale wind farms. And I'll show you example to I'll show this example to you to show how the how the skills you can get in physics are so transferable to many, many, many areas. So again, if you're in grade 10 or 11 or 12, if you don't know yet what it is you're going to do, that is perfectly fine. Just keep your doors open. Take math, take physics, computer science, chemistry, and then you can decide. Just make sure to keep your options open. On our campus, for example, we have courses in person and online. A lot of our core classes are online, which also adds flexibility. So sometimes students spend the semester studying from home, or they can actually move between campuses. And this is my lovely research assistant. I work from home quite often myself. So my cat is keeping me company. So thank you so much for joining me. It's been a pleasure. If you have any questions, this is my email, sbarkanova@moon.ca. And thank you so much. Thanks for joining me.